Every age has its rulers. Every period in the 4 billion-year history of life on this planet has produced a dominant form. A creature or group that seized available resources, solved challenges, and imposed itself with completeness and confidence. We know the rulers of the land, the great dinosaurs. Apex predators and massive herbivores thundered across Mesozoic continents. They ruled for 160 million years, leaving bones and rock for us to find, study, and stand before in mute astonishment. We know the rulers of the sea, mosasaurs, plesiosaurs, and ichthyosaurs. Great marine reptiles filled Mesozoic oceans. They brought predatory life of extraordinary scale and ferocity to the deep. But there is a third kingdom. Most people give it only a passing thought when thinking of the Mesozoic world. A brief acknowledgement, a mental image of a leathery winged silhouette against a Cretaceous sky. That kingdom is the air. The creatures that ruled it own the Mesozoic sky with completeness. Their biological sophistication is consistently and dramatically underestimated by popular imagination. They were the pterosaurs, not birds. Not ancestors of birds. Something entirely separate, entirely independent. In many of its most extreme expressions, entirely without equal in the entire history of vertebrate flight. The pterosaurs were the first vertebrates ever to achieve powered flight. They ruled the air for over 160 million years, longer than the dinosaurs ruled the land. They produced, in their final evolutionary chapter, animals so large that the engineering of their flight still challenges modern science. They did all this extraordinary biological achievement, all this aerial dominance across geological timescales, without leaving a single living descendant. They are gone so completely, so finally, and so without biological legacy. The sky they once ruled shows no trace of their passing. That absence is one of the most profound silences in history. Segment 1, the first ones to fly. The origin of pterosaur flight is one of the great unsolved mysteries of vertebrate paleontology. Not because the evidence is ambiguous, but because the fossil record of earliest pterosaurs is frustratingly incomplete. The transition from ground-dwelling ancestor to fully capable flying animals is a gap that has resisted every attempt to fill it. What we know is this: pterosaurs appear in the fossil record approximately 230 million years ago, in the late Triassic period. Already fully capable of powered flight, already in possession of the complete suite of skeletal and soft tissue adaptations. With no transitional forms, no half-developed wings, no intermediate stages preserved in the rock. They arrived in the fossil record as if from nowhere, fully formed and fully functional. They immediately began doing what they would continue doing for the next 160 million years, dominating the air. The wing of a pterosaur was not built like the wing of a bird and not built like the wing of a bat. It was a membrane, a thin, highly vascularized sheet of skin and muscle and elastic tissue. Stretched from an enormously elongated fourth finger of the hand to the body, and in many species down to the hind leg. Supported and controlled by a complex arrangement of muscles and internal fibers that gave precise and dynamic control. Modern aeronautical engineers recognize this as a solution of remarkable sophistication. The single elongated wing finger, the defining structural feature of pterosaur flight, was not fragile or limiting. It was, in the largest pterosaurs, a bone of extraordinary length and strength, bearing aerodynamic loads, whose wingspan exceeded that of any bird that has ever lived, and whose flight performance was far more capable. far more versatile than the popular image of a slow, soaring, gliding creature has ever given it credit for being. Segment 2. A world full of wings. For most of their 160 million year reign, pterosaurs were not the animals of popular imagination. Not the enormous, slow-moving, cliff-perching giants that most people picture when the word pterosaur is mentioned. For the vast majority of Mesozoic time, pterosaurs were diverse, ecologically varied, and in many cases surprisingly small. A radiation of flying reptiles that filled the aerial niches of the Mesozoic world with thoroughness and creativity. The earliest pterosaurs of the Triassic and early Jurassic were mostly small to medium-sized animals. Some no larger than a modern crow or a small hawk, with long tails that they used for aerial stability, teeth in their jaws for catching fish or insects, and a variety of body forms. Reflecting the variety of ecological roles, they were already beginning to partition among themselves. As the Jurassic gave way to the Cretaceous and the world below grew more complex and competitive, the pterosaurs themselves underwent the most dramatic evolutionary transformation of their long history. A transformation that produced, in the final chapter of their existence, the largest flying animals this planet has ever seen. The long-tailed early pterosaurs gave way to a new group, the pterodactyloids, that were shorter-tailed, longer-necked. In many cases dramatically larger than their predecessors, exploiting a range of ecological niches, extending far beyond the fish-catching and insect-hunting lifestyles of the earlier forms. Some became filter feeders, straining small organisms from the water with comb-like teeth. Some became specialized fish hunters, diving into the water from the air with the precision of a modern gannet. Some became scavengers, soaring on the thermals above the Cretaceous landscape on wingspans that grew, generation by generation, toward dimensions that make the wingspan of the largest living bird look, by comparison, almost modest. And some, the largest, the most extreme, the most extraordinary of all, became something that the history of vertebrate flight had never produced before, and has never produced since. They became giants. True, almost incomprehensible, engineering-defying giants. And the most extreme of all of them had a name that has become, in the world of paleontology, almost synonymous with biological impossibility. Cliffhanger, end of Part 1. 160 million years of aerial dominance, built on a wing design no other vertebrate replicated. Diversifying across the entire span of the Mesozoic into a community of flying animals of extraordinary ecological variety and biological sophistication. And then, in the final chapter of that extraordinary story, something happened. Something that pushed pterosaur evolution beyond every boundary that had previously constrained it. Something that produced animals so large, so structurally extreme, and so aerodynamically improbable, that when modern scientists first attempted to calculate whether they could actually fly, the numbers came back wrong. In Part 2, we meet the giants. We stand beneath the wingspan of Quetzalcoatlus, and we attempt, with every scientific tool available to us, to understand how something that large ever got off the ground. And we discover that the answer, when it finally comes, is more remarkable than the question. There is a moment every paleontologist describes, not in the field, but later, in a quiet lab or office, when measurements are taken, calculations run, and the full reality of the fossil is assembled. It's the moment you realize, with clarity, that what you are looking at should not exist. This animal's remains, carefully catalogued, appear to violate physical constraints for flight. No modern flying animal comes close to its capacity. That moment is the Quetzalcoatlus moment. Quetzalcoatlus northropy was first described in 1975 from fragmentary remains in Big Bend National Park, Texas. Even from incomplete wing bones, its enormous scale was immediately apparent and startling. Decades of analysis refined the picture, revealing an animal of extreme dimensions. Simple numbers cannot fully convey the reality of its immense size. Its wingspan was 10 to 11 meters, like an F-16 fighter jet. Wider than a double-decker bus, wider than the Wright brothers' first aircraft. On the ground, it stood 5.5 meters tall, like a modern giraffe. Its neck alone was as long as a large horse's entire body. It weighed 200 to 250 kilograms, the heaviest flying animal ever. The immediate question was, how did it fly? Not whether it flew, but how. By what mechanism, what combination of power, principle, and strategy did it get airborne? And once airborne, how did it sustain flight over such vast distances and altitudes? Segment 2. The science of the impossible takeoff. Decades of research reframe what we knew about large pterosaurs. Quetzalcoatlus did not take off like a bird, running or leaping from cliffs. Its skeleton points to a different, more dramatic launch, the quad launch. This extraordinary biomechanical engineering used all 4 limbs simultaneously. An explosive, pole vault-like movement, launching it into the air with velocity. The forces involved were enormous, several times its body weight in a fraction of a second. Its wing bones were hollow, thinner than a playing card, for strength and minimal weight. The entire skeleton weighed less than most large dogs, a feat of biological engineering. Once airborne, Quetzalcoatlus was an extraordinarily efficient soaring animal. Using thermal updrafts like modern vultures, but on an unprecedented scale. It soared to altitudes and covered distances no modern bird can approach. Capable of sustained flight at 4.5 kilometers, 120 kilometers per hour, over 16,000 kilometers. Transcontinental journeys in a single flight across the Cretaceous world. Segment 3. The ecology of a giant. Quetzalcoatlus was not only a flying machine, but a living, hunting, complex animal. Its ecology challenges the image of a fish-hunting, cliff-dwelling, ocean-skimming predator. The Big Bend fossil site was an inland environment, hundreds of kilometers from the coast. It was not a seabird scaled up, but something stranger, a terrestrial predator. It spent significant time on the ground, moving efficiently on all 4 limbs, using its enormous neck and spear-like beak to probe and strike at ground prey. Like a modern stork or secretary bird, but at a scale unmatched by any bird. Capable of taking small dinosaurs, juvenile hadrosaurs, large lizards, and mammals. Anything its reach and predatory intelligence identified as a viable target. Quetzalcoatlus was genuinely without parallel in the modern world. A flying animal the size of a giraffe, hunting on the ground like a stork. Taking off like a pole vaulter, soaring like an albatross. Navigating the Cretaceous world with aerial and terrestrial versatility, making it one of the most ecologically versatile predators of its time. And it was not alone. The Azhdarchid family produced multiple species of giant flying reptiles, each a variation on the extraordinary theme of gigantism and ecological versatility. Cliffhanger. End of Part 2. Quetzalcoatlus, the giant that should not have flown and flew anyway. That should not have hunted on the ground and hunted there with devastating efficiency. that should not have crossed continents in a single flight and crossed them anyway, defying the physical limits every model of vertebrate flight had previously imposed. But the story of the giant pterosaurs does not end with Quetzalcoatlus. Across 160 million years of pterosaur evolution, other lineages produced their own extremes, their own biological impossibilities, their own answers to what a flying vertebrate could become. In Part 3, we meet the others, the bizarre, the spectacular, and the deeply strange. We explore what the fossil record tells us about flight and biological possibility, and confront the question of what was lost when they died and what the sky has been missing. The giant Uzdarchids, like Quetzalcoatlus, are pterosaurs that stop conversations and make jaws drop. They provide the scale and drama needed to convey their 100- and -60- million-year tenure in the Mesozoic sky. But to understand pterosaurs fully, you cannot stop at the giants. We must explore their other lineages. Their evolutionary creativity produced bizarre and structurally extreme forms, unlike conventional flying reptiles. They raise questions about evolution itself, how far natural selection can push a body plan. Tapejara, from early Cretaceous Brazil, was a medium-sized pterosaur with a 4-meter wingspan. It was distinguished by a cranial crest of extraordinary size, one of the most dramatic in the fossil record. Tapejara's crest was a vast sail-like structure supported by bony prongs and brightly colored skin. Its head was larger than its body, so disproportionate, scientists debated if it could fly. It could fly. The crest was largely hollow, a lightweight structure of thin bone and soft tissue. It functioned as a display for sexual selection, like a peacock's tail, despite its aerodynamic absurdity. Tapejara, another Brazilian pterosaur, carried a similarly enormous crest, but with a different geometry. Its fan-shaped structure swept backward in a smooth curve, giving it a unique profile. Pteranodon, well known, wore its crest pointing backward from the rear of the skull. This crest may have functioned as a rudder, allowing fine control in its soaring fish-hunting lifestyle. Nyctosaurus, a smaller, lightly built pterosaur, carried a structurally inexplicable, antler-like crest. This crest had no soft tissue membrane or clear aerodynamic function, a true evolutionary enigma. It reminds us that evolution doesn't always produce what engineers would design. The diversity of pterosaur form is not merely a catalog of biological curiosities, it is a lesson. A lesson about flight itself, about what it demands and what it makes possible. Pterosaurs flew for 160 million years across a wider range of body sizes and niches. They explored more structural solutions to aerial locomotion than birds or bats combined. This extraordinary experiment demonstrates that flight is not a single thing, but a space of possibilities. Pterosaurs explored the lower boundary, small, agile forms hunting insects with precision. They explored the upper boundary, the giants, aeronautical impossibilities our models struggle to account for. They explored ecological dimensions, fish hunters, filter feeders, terrestrial stalkers, and ocean crossers. Each was a different answer to what a flying vertebrate can eat, live, and organize its existence around. They demonstrated that the limits of what life can do are always further away than we think. Evolution finds a way to redraw boundaries, and pterosaurs redrew them over and over again. 66 million years ago, the asteroid struck, ending the dinosaurs and collapsing ecosystems. This same event ended the pterosaurs, not at once, but in the months and years that followed. The food chains that sustained the Mesozoic world came apart from the bottom up. Pterosaurs were already a reduced group, with birds occupying niches smaller pterosaurs once held. But they were still there, still flying, still soaring on the thermals of the late Cretaceous world. Then the sky went dark. Thermals collapsed as Earth's surface temperature dropped. Fish populations crashed, and terrestrial prey disappeared as ecosystems disintegrated. One by one, the last pterosaurs ran out of resources and died, falling from the sky. They had ruled this sky for longer than any other flying vertebrate in history. The sky above us today is full of birds, nearly 11,000 species. Yet the sky is empty in a way invisible to us, because this absence predates our species. But the fossil record knows. The rock remembers a sky with the largest flying animals. A third lineage, ancient, diverse, and biologically innovative, has never been replaced. Quetzalcoatlus is gone. Tapejara is gone. Pteranodon and Nyctosaurus all gone, leaving behind nothing but bones and rock and the ghostly outline of a wing membrane, and the silence of a sky waiting for something large and strange enough to fill the space. Nothing has, not yet. Perhaps nothing ever will, but the pterosaurs were here. They ruled this sky for longer than we can truly comprehend. They pushed the boundaries of what flight could be further than any creature before or since. Their story, written in hollow bone and membrane, is one of the greatest in life's history. A story that belongs to our understanding of what life is, what it can do, and how far it will go.